Thank you very much. Gracias, comme on dit ici. I'm very pleased to be. Também, yes. Bom dia. Unfortunately, we've got to speak English, yes. So I don't know if there is any British here, but okay, we are already. So I'm very pleased to be here. Now, actually, I know you will be very frustrated. I am personally, because we are still in the business with Rosetta, and so first of all, most of the things have not been acquired yet, and essentially what has been acquired we're not even supposed to tell. So because of this stupid embargo stuff. So I will try to make a mix of that. And if we were not recorded, it would be much better. But we are stupidly recorded, so we can't. If I say something from another PI and he will know on his screen that something has been said that I should not, you can imagine. Anyway, I would have preferred personally to talk on something different, because habitability is really something I love. I worked on Mars a lot. And I am strongly against the concept of habitability. And for me, if something is habitable without being inhabited, something was missing, so it was not habitable. So either it's inhabited or it's not. Anyway, okay, let's drop that. I will go back to that. So for those who want to contact me afterwards, I'm at EAS close to Paris. And just to remind you the context of what I'm going to say. So the launch was more than 10 years ago, so just for the time scale. We were in cruise during 10 years, essentially, and the decision was even 10 years earlier than that. And you will, in a moment, understand why I would like to put some history there. So it's an ESA mission, and what I put here, it's the fact that in the old Horizon 2000 program that was born in the 80s by Bonnet and Al, we had 4 cornerstones. And at that time, SO and XMM were launched, and the question was, okay, which one would be number 3, which one would be number 4 between Rosetta and FIRST? FIRST actually became Urchin and Planck, and the decision taken by ESA in November that Rosetta would be the number 3. So it was by 93, more than 20 years, that we decided this mission. But actually, to understand the context, you've got to realize that really, this mission was born 10 years earlier, which was at the time of the first ever flyby of a comet, and that was in '86. 5 probes were there to rendezvous with the comet Halley. But actually, it was not a rendezvous, because at that time we didn't know how to slow down sufficiently to follow the comet, so it was really a flyby. And the velocity of the flyby was 67 kilometers a second. So when you are on front, and here in between you have 2 minutes to deal with. So it was really 2 minutes observations. And it was a fantastic observations really made at that time. It was the early time of space exploration when you really realized in '86. We had to prepare that by the late 70s, early 80s. So really it was the very first things. And there was 2 Soviet probes named Vega, V like Venus, because we had to first go to Venus and then to go to Halley, Ga by Gale. And it was the first time ESA ever went to space by out of the Earth. It was the Giotto Mission. And what happened is that the first, it was very successful. We went very close to the nucleus. Close means that the Vega went something like 10,000 kilometers, and Giotto even less than 1,000 kilometers. And it was plenty of discovery there, essentially because this image that everyone knows translated something very important, is that although the comet was, as we expected, made essentially of water ice, because we knew that for a long time, 80% of water, essentially, you saw in the coma, and we discovered the same. We had an infrared spectrometer there that showed this is the first ever spectrum found of a comet, when you have the emission here line in infrared, H2O is here. So it's essentially made of ice, but against all the prediction, and that was really why it was a huge discovery, the albedo was obviously very, very different from what we expected. It was less than 5%. We thought that getting to an icy body, it would be very bright. It was the darker ever seen body in the solar system. 3% albedo, essentially, depending on the wavelength. So it was really charcoal things. And the question was, okay, why that? And the answer went in part with a sort of spectrum. We understood that most of the carbon-rich material which had this bond. That was the only feature we had. It was like CH, but not CH4. You might remember that the question at that time was whether or not what we call the parent molecules of what we saw in the comma were essentially CO2 or CH4, and that has to do, of course, with this question of million-year things. We knew that CH4 would be more favorable for evolution towards amino acids. And the question was, okay, because it's made far away, although in the inner solar system, CO2 dominates in Venus, in Mars, and in the Earth, we know early times. It's the opposite there. And the question was, okay, because the comets formed there, is CO2 or CH4 the dominant carbon-rich species? And so the answer to that went rapidly. And rapidly means that when we had the possibility with the mass spectrum to observe the grains, even at thousands of kilometers from the nucleus, that's a typical spectrum that we made, and that's an expansion of that, and that the famous CaO, half of the grains were made only of CHO and N atoms, the famous Schwann particle. It was really unexpected that most of the material there, even grains which were micron-sized grains, so it could be 10 to the 12, 10 to the 14 atoms in a single molecules, were only organics, essentially. That was really a big discovery. And that just tells you that story. And so we knew that we had something very specific, and now it's almost trivial, but at that time it was not really trivial to realize that comets actually sample the collapsing protosolar cloud at the end of the collapse. We knew what a molecular cloud, we knew already, of course, what a molecular cloud was, because we observe that in radio waves, but when the density are typically 10 to the 3, 10 to the 4, 10 to the 5th molecules per, or atoms and molecules per cubic centimeters, here we have 10 to the 10, 12, 15. So we have no idea what the endpoint of the collapsing clouds was in terms of the physics and the chemistry, and suddenly we realized that the comets are the only bodies who really sample that cloud. And most importantly, we understood that. So I understand also that for the bottom side, you don't see what is here. So I will just translate that for the others. We have a lot of organic there, and the organics are neither CH4 or CO2 dominant, but they are dominated by these large, complex refractory molecules, which are very stable, but, and this is the important point, formed during the collapse itself, during a very specific chemistry that no one can simulate, or no one could simulate at that time. It's an ion molecule grain interaction with the cosmic rays, probably the sole energy source here. And these really end with a very specific load of organics in the ices. And when you put these molecules in the ices are essentially dark. And so that caused the albedo of the comets to be so low. So that was the very first time that we realized that most of the what we call the parent molecules, which really are made by the collapse of the cloud itself, were born at that time. And of course, the question was whether or not these organics may have played a role afterwards. And that really was only emerged at that time, I would say 87, 88, when a few of us really realized that these molecules embedded in the ice then can play a role afterwards, essentially because, of course, they can feed the oceans, planetary oceans. But, you know, the fact that H2O comes from a comet, it's funny, but no more than that. The fact that if it's come from a comet, a few percent of the molecules, of the water molecules, are really these organics. And the question was whether or not these molecules could not be the famous missing link to that, or at least the enabling link. These molecules, because of the specific of the chemistry, may be much different from the suite of molecules that you have by the normal Miller-Urey sort of analysis, where you can, the variety of amino acids in this Miller-Urey is too wide, actually. And this chemistry might be specific enough to have enabled the emergence of life. So the question, of course, was, okay, is that really the case? And that really is almost 30 years old as an idea. Of course, more than 25 years from that point to now, and a lot of things have changed meanwhile. And this is why when we decided, as you will see, the Rosetta Mission at that time, we decided on a goal, which was essentially what I explained now, to try to have access to this carbon chemistry. And of course, we add a lot of things afterwards because meanwhile, the context has changed. And if it has changed, essentially, it is for something I will stay 1 minute there because to me, it's really, I'm very sensitive to that. The question is, we had 20 years of space exploration, and this space exploration during 20 years has really changed a lot, to my mind at least, the way we have on the evolution of the Earth on the planet themselves, in particular because we have exosystems discovered. At that time when we started that, we didn't even know that we would discover the exoplanets as they were here. And the question is whether or not these processes that might have made these complex molecules key for the life afterwards, if these processes, are these processes generic or specific to our solar system? And this is something that we had no idea at that point. And if I said that generic or specific, remember that at that time, which is 30 years ago, the dominant ideological really load we had on the shoulder was this question of priority of worlds. If you had that sort of audience 30 years ago, and you asked the people, is life present elsewhere, everyone would have answered yes, because at that time, everyone was convinced that the Earth was not specific, that planetary systems are just spread over the entire universe, not infinite, but almost. And so what we have here necessarily is from somewhere else. It has to do with the ancient time, Democritus, Epicurus, and then Giordano Bruno and all things that passionately built on this idea. It was dramatic what happened in Italy in particular with Copernicus and Giordano Bruno, who, as you know, was burned to have said that necessarily the Earth is not specific, and there are an infinity of worlds at that time of Earth. And really physics paved the way to put that idea as really the dogma up to the time. Remember that when the Viking mission were launched for 76, the question was not to search for life there, but to characterize the life on Mars. The question was what sort of metabolism we have there, whether it's O2 given CO2 or CO2 given O2. These were the instruments on board Viking. Because so convinced the people were that life is present everywhere. And when we launched this mission towards Halley, it was exactly the same. So really, this question of priority of worlds was really the basement of all the way we thought the universe was. But then, of course, we have discovered that there is what I call a fundamental diversity. It's not that just by chance the planets are different. It's that the way the evolution of the planet goes now is understood as necessarily bringing diversity there. You cannot have it here. It's not that the Earth is different from the other that would be similar. Earth is different from Mars, which is different from the others. They are all different because now we understand that the processes responsible for the evolution of the solar system made that diversity basically, fundamentally. And so this is true for the evolution pathways. For example, I just put one here, the question of water stability. If 30 years ago you would have asked, is the stable, liquid water stable on the planet something generic or not? Everyone will say, of course, yes. Now only we understand why. Only on Earth you could have preserved liquid water as a stable constituent on the surface. We start to understand now the history of the water on the Earth, and thanks to that we understand why on Mars, for example, supposedly it happened, and we think it happened on Mars, but only during a very limited time. We understand why on Mars and the Earth the pathway diverged rather soon after the planet formed. So we understand that the early habitability of Mars possibly had to also fade out very rapidly because of many things we could explain there, but it's not the topic here. So, and of course, at the same time, we understand that looking at exoplanets, we have exactly the same sort of thing, that diversity is really the rule. It's not, again, that our solar system is different from the others, it's that everyone is different from the other. And this question of diversity is fundamental here. And again, what I put here is not that we have specific processes here. That's, as processes, they are, of course, generic, the same sort of interaction, the same collision, the same sort of things. But the forms they have is such a variety of possibilities that drive the diversity. And so now only, we understand that really if you want to realize why life started on the Earth and possibly not elsewhere, you have to understand what are the sequence of processes that led to the Earth as it is here. And as you will see, Rosetta is right there. So that's what I said. An example of what has not been discussed this morning yet, I understand from what has been said and what will be said during this meeting that, okay, all this question of creation and migration, whatever, is now sort of well understood, at least in terms of the assumption you have to deal with. But, for example, the nature of the specifics of the way the central core will accrete toward the sun, toward the stars. The time constant of that evolution will be a fundamental driver of the rest of the evolution. I put only 2 or 3 things here. the question of whether or not the UV field of this collapsing cloud will be polarized or not is fundamental, because we have demonstrated that if, depending on the way the magnetic field of the star will behave, the part of the field, the UV field, is polarized, then you will immediately build some extra fluctuation that will lead to chirality things. And that has been demonstrated rather clearly. And so the way the sun itself will collapse might have a role in the way the chemistry will behave afterwards. The same for the solar wind. No one still have understood or taken into consideration that as soon as you have a Titoris type solar wind, grains down up to centimeter scales are just swatched away. And so you've got to accrete very rapidly things if you want to take rid of that. So again, a lot of things might be specific to the way our cloud will behave. And it's not because in our cloud we have a specific chemistry that happened that it will be generic by itself. And you have processes after processes the possibility to understand that finally we have a given endpoint, which is what we are here, but there is no necessity for that sort of endpoint to be equivalent somewhere else. So Mars 96, we have these, and obviously the importance of this material was so that all the agencies, I put NASA and ESA, but actually the Soviets were involved also. We wanted that next mission would be to go to a comet, take a piece of ice, bring it back here, analyze it. And that was the famous cometary nucleus sample return. And that was really the core of what we wanted, and still want actually, as the next step of exploration. And that was built, and during a year or so, everyone worked on that. And of course, as very often happens, NASA decided to withdraw even without making a phone call. And so ESA was left alone, essentially. And we said, OK, we can't, with the budget we have and the capability we had at that time, we couldn't go to a comet. We know now it's not trivial to land on a comet, but to get out of that with a two-stage rocket automatically, it's not trivial. So we decided not to do that. And actually, Rosetta was decided as a mission that instead of getting then returning samples, we'll do the opposite, build a lab and put the lab over there. And this has been Rosetta, and that was decided in '93. So that was the sequence of things that we decided at that time. And the goal were to perform a thorough exploration of a comet, both around the comet by remote sensing, also in situ in the coma, and by landing. It was not trivial to saw that, and these are all the goal that I expanded here. And again, on top of this question of the organics, which might have played a key role in the emergence of life, there was this question that went more and more importantly to understand the processes and the ingredient that led to the diversity of the solar system as it is now. And we knew that the comets, in principle, would be the best bodies having recorded and preserved up to now most of what we are interested in, for obvious reasons. I will go back to that. And the last point I put here is, again, this question of generic and specific of that. So that was really the goals. And to do that, what we do want, have access to the composition, the processes, the internal structures, and all what is involved in the activity. So that was really the entire set of the suite of things we wanted to do. And it led to something which is on the order of 10 instruments, plus the lander, which was named Philae. Just a few words on Philae at that point, to say that Philae was not, although it's understood as such, it's not an ESA system. It's not that Rosetta included a lander with an AO to put instruments on board. It was not the case. Unfortunately, for reasons which have to do with the way it's been decided in '93, for this mission to be number 3 in the Horizon 2000, the lander was proposed as the other instrument, as an instrument really, within the AO. You were eligible to propose a lander. And if you want to propose a lander, you had 45 kilograms as an 11 instrument. And a few of us proposed that. And actually, after a few months, it was obvious that all the people involved in building the, what we call the SSP, Surface Science Package, could not work independently, really, and we tried to merge. I could also say that after a point, there had been 2 landers, one led by the Germans, Lindau, Helmut Rosenbauer, and the others were a joint venture between JPL and ourselves in France. It was named Champollion. And of course, what happened that after a while, NASA decided to withdraw without making a phone call. And so the Champollion collapsed. And that was a chance because thanks to that, all the European countries decided to merge. And that's how Philae went. But Philae is really the result of that building. It's been built by a few people building a consortium with 3 agencies which are listed here, ASID for the Italians, the Germans, and CNES. And on board, we had an AO and 10 instruments on board. So during Philae, we had not only to build the instrument, but also the entire system that will land, operate with all what a system can do, with energy, CDMS, whatever it is. And that explained, but we had a very limited resources, actually. Good, so that's what has been embarked finally with Philae here, but all the other, the 10 instruments. And most of what you have now is the result of the operation of all of that without this, because this, as you will see, has landed. This in itself is, so it's not an instrument, it's an instrument plus a system. And I will go rapidly to what we do afterwards. Good, so the challenges to get there were really enormous, essentially because what we wanted to is to analyze this material prior to the sun to potentially modify it. And so we wanted to do that at far distances. We want to have a rendezvous so that we will land at 3 AU. To land at 3 AU, and because we wanted to land and make a rendezvous, we had to go behind the comet and slow down to be exactly at the same speed of the comet afterwards. So we had to build a system which would go up to 5 AU, even beyond 5 AU, and then slow down, and that happened. And we have, as you know, in Europe only, we don't have RTGs, we have only solar cells for the electricity. So it's a huge system. Would not enter this room. This is 60 meters square of solar panels, never done before. And we have the same, not the same size, of course, the same energy on Philae itself. So that was really the point, because we wanted to analyze the system at 3 AU. That 3 AU means that the temperature, when we would operate, is lower than minus 150 probably. And so we had to build instruments capable and a system capable of surviving in that temperatures, which was not trivial. So when I say unprecedented challenge, it's true. The images, as you will see in a moment, have been built by camera that we built actually in our lab and with partners, of course. They operate at minus 150. Minus 150 degrees, you have a CCD working just normally without any problem. So we had to build that, and that was complex. So the very first things which happened, as you might know, was it was actually July 14, and when we discovered for the first time this comet. And when we discovered that, and we said, well, it was awful, because when we discovered that finally what we had chosen as a target, which was essentially chosen by the orbiter, the orbit was just complying with our capability to meet and rendezvous with. When we observed last July that was the body on which we would have to land, it was awful. And so the closer we went, it was even worse, because when we saw the surface itself, we said not only it's rotating in a very odd way, but then it's full of cracks and everything, and we're very limited for the landing in the sort of slope we have when we land. So it was really sort of but finally, by the end of August, early September, we had only 2 months to decide on the basis of all what we could acquire with the data, whether or not we would be able to land and where to land. And we have selected one place here for different reasons that I will not elaborate on because time is running, but if you have any question, of course, I will be happy to answer that. And so a few results by these 3 instruments first, OSIRIS, VIRTIS, and ROSINA. OSIRIS is the camera, VIRTIS is an infrared imaging spectroscopy, and ROSINA is the in situ mass spectrometer. Not to say that the others have not really worked, but most of the results acquired up to now actually and published were acquired when the distance were above 3 AU. It was essentially the results acquired from August to October last year. And so most of the other instruments could not really operate because the in situ measurement for the grains, for example, the density of the grains are not sufficient. They will now enter the phase. I've not said that, but we are presently now a little more than 2 AU from the sun, and we will reach perihelion August 13 this year. And so at that time we'll be close to 1 AU. So we are still rather far away. So a few things. First of all, the images. They are absolutely spectacular because no one would have expected that a cometary nucleus would be like this one. Actually, we never went so close, capable of really making the global mapping of that. So this is part of them. When we increase, of course, when you stress dynamics, we see the outgassing, as you see here. And so this is normal, but again, it's rather misleading because the amount of water which is escaped there, it's really very limited. It's very low. It's a very low activity that we have here, but still. And the question, of course, that immediately went is that the result of a collision of two bodies making only one? And that's a possibility. Or is it exactly the opposite, that one is becoming two just because of the fluctuation of erosion that will increase essentially the erosion in the middle here? I would say at this point, we don't have the answer yet. We have put in place, I think, all the measurements that will solve the issues in the coming months, for sure. That it has a lot of importance here because that will tell us something about the dynamics of the cloud. Because these, I have no put the scales here, but this is, sorry, okay. This is typically 2 kilometers here. That's 4 kilometers here. So it's about 1.5 to 2 kilometers here. So that's the sort of body we have here. And the question is, do we have kilometers bodies capable of interacting with that sort of size? And both are possible. At the very beginning, like in October, everyone considered that that would be the what happens here. But the problem we have is that the axis of rotation is somewhere here. And so this point here that I will just show now, the view from the other side here with fantastic cliffs here that you can see here, is the least, already 5 minutes? Okay, so I won't finish my sentence. So, okay, to go rapidly then. No, but the idea is that at the beginning we thought, just to finish the sentence, that the question of separation into two would be the case. Now the people consider most likely that that's the opposite, that we had collision in kilometer-sized blocks, but at very low velocity. So we do not have really a lot of effects of these collisions. I might go to that. So, but when you see the structures, you see a lot of things like this one, for example. And if I stay there half a second, it's just to tell you that be careful, these are not impact craters. And there is not, everything is really driven by activity and only activity. These are probably just due to the fact that it's a very porous material. The density is lower than 0.5. And so as soon as you have sublimation, you make voids. And just because of the voids and the very little gravity is sufficient just for the material to fall on. So most of the people believe now that these are made by the activity and these are not crater things. And there is different observation that goes in that direction. So they are essentially activity-driven and not impact. So it's a very early accretion because you had, in the accretion process, to ensure that this body will never face afterwards any impact regime. And this is not trivial. So not only you have to make these bodies rapidly, but because essentially you do not see a lot of big, of course there is small craters there, because accretion means also distraction. But most of the structure you see mean that you had to make these bodies migrate and go to far reservoir very rapidly. They are not. And that's something that was not obvious because people thought that, all these questions, comets and asteroids. No, essentially there is a big difference here. We do not see any big evidence for cratering at all here. And importantly, you have a global grain cover. So different facies in there. But you see that, again, there are places out of which you have grains over there and essentially no structure here. But what is important that when you go to the composition of that, and this is by the Virti things, whether you go in a place which is rather smooth or other words, the spectrum is essentially the same. And I will stay also half a second on this spectrum because the spectrum is important. The two places here are the two places in which normally spectrally you should see water ice. There is not a single spot on this comet, as seen from the moment. We know now that there are a few, but very limited, in which to see the ice. Although it's, again, predominantly made of ice, there is no ice at the surface at all. The surface is entirely covered by something very dark. The albedo is almost homogeneous. It's, that sort of images misleading because you see it's very bright. No, it's just you stretch the dynamics. Even the bright places here are 5% in albedo. So all this, whether you are here or there, has essentially the same albedo and the same composition. And the composition is not driven by the water ice, but by this feature here. And this feature here essentially is the famous 3.1 to 3.3 micrometer carbon-rich feature. For the moment, Virtis has not been able to identify by the position here whether it's aliphatic or aromatic. As you know, 3.2 and 3.4 make a difference there. For the moment, there is no difference. We see only this big overlap, and it is the same everywhere. So when we saw that, we were sort of happy. We said, okay, wherever we land, we will have this carbon-rich material at hand, because that's, again, one of the goals we have to analyze that. And so that's the very first result which have been found. There is a global cover of carbon-rich material there. We didn't know the scale at which the material would be homogeneous, because when you see from far, you have no idea whether you have patches of water, patches of dark material. No, it's intimately mixed. Whatever the scale you look at, up to this sort of scale, which is meter scale typically, or tenths of meter, a few meter scale, you do not see any patches of water ice. It may change when we go closer, of course, and when the activity will be different. Good. Rosina has seen for the first time up to October and November a variety of compounds here. It's published, and you may have access to that already. What is important there is that, first of all, you have a lot of nitrogen-rich material, more than what you put here. There is nitrogen here, also a lot of sulfur, and many mixtures of that. Actually, the list of these molecules are much more longer than these ones. But be careful. These were measured up to typically November, December. We were above 3 AU at that point, or close to 3 AU. It might not represent the bulk of the material. The same for the D/H ratio, which has been published early on. It was a D/H ratio measured in August and September. That was essentially, and I will go back to that, to something that might represent the upper crust, not necessarily the deep interior. So be careful. Most of the material, again, or most of the results that will be acquired now might differ from these. Good. So first set of results. Indeed, it's one of the earliest solar bodies that we wanted to have. That was what we wanted to. It suffered very limited processes except for surface outgassing. It should have preserved the properties of the collapsing cloud. It's a very low density icy body, and it's loaded with dark organics. So that was weird. But of course, we had to wait until philae would land and then to go closer to it. And so that's where I am now. So, first things. We had put, it was the idea we had at that point was to put cameras. When you want to make a panorama, what the Americans do, for example, on Mars, they have a mast, a camera, and then they rotate it. We consider it stupid to do so because you have 1.5 kilograms of mechanics for a few tenths of grams of detectors. So we prefer to do the reverse, to make very small cameras and put them all around. So that's why we developed these micro cameras. We did at that point, and what you saw here, that we have 7 cameras all around. These are the field of use. And we named that Shiva because of the god, of course, a lot of bread, a lot of arms, and only one brain, which is exactly our system. And that's one of the things that I love that sort of thing, because we were still attached. And what you see here is Rosetta. We are philae right here. We are on philae. We are attached to Rosetta, but we have the solar panels over there. Again, 15 meters of solar panels. The sun is on the other side, and the reflected sun that we have here, these are the electrical connections. And this is the body we wanted to have access to. And so this shot was September 8. We were at 50 kilometers at that point. And we did that a month later, so that was before and after. We were closer, 20 kilometers. And I like this one very much because that's exactly the distance out of which we've been released a month later. We've been released from 20 kilometers. The descent, the freefall descent, was a 20 kilometers freefall descent. A little more, 22 kilometers freefall descent. So that's exactly where we were launched. And so we wanted to get there. And again, that's the place we had selected. The next slide, you can, that's the reason why we did that. And this is the 1 kilometer, that's the sort of size we had there. I have not time to explain to you why we have uncertainty, but really at that point, the bigger risk we had was to miss the comet. And from 20 kilometers, if the velocity vector is a little different in position or in attitude pointing than the one you have, you just go above or beyond, but you are not attracted because there is no gravity. So really, that was the issue here. So we had a dream and a plan, and these, of course, artist view. We wanted to be separated like that. We hoped that at one point we would be like that, and then landed. We also had the dream that after landing, we would deploy everything, the feet, the antenna, the boom of the magnetometer. These are the concert antenna to make the tomography. We wanted to have that. We had no idea whether or not after 10 years in cruise we would succeed in doing this. And finally, but this picture went rather long afterwards, days after, well, the next day. These are splendid images taken by Osiris from the orbiter just after we were released. But we got this image only the next day. And it was very spectacular because we saw on this image that the feet are deployed, the antenna is here, and the boom is deployed with the magnetometer. So at least these worked. And these, we had the possibility to make decent imaging. Actually, from this one is the farther away, 67 meters prior to touchdown. We have a system that every few seconds we take a mini image, like a ring buffer, and it will stop at touchdown, and we would keep the last 7 images. And that one, the first of the 7 images, the last one is at 7 meters. And actually, these, during all the descent, we had this, and this exactly where we should have landed, and actually that's where we landed. I will not show you the last images because of the record, but we had the entire set of images there. And so that's exactly where we were, 100 meters from the target point, which is really spectacular if you realize that we are 500 million kilometers from the Earth. I put that, it's not really, it was not trivial. And again, it was really complex. And so when we had that, of course, we were very happy because we had a signal there, we drank champagne, whatever, and then we had planned the first 10 hours of observation afterwards. And the very first thing we had to do after 5 minutes was a panorama just to see where we were. So I climbed the stairs to get the first images, and this is the first images I got. And that was awful, because these images, although I knew that our camera were doing well, it was obviously we were moving at the time. 5 minutes after touchdown, we were moving. And so it was awful because we didn't know where we were. And the question, okay, had we rebounded with a velocity higher than the escape velocity? We touched down at a velocity at 1.1 meter per second. The escape velocity is 0.7 meter per second. So if the rebounds were at 0.8 or 0.9 meter per second, we would never have come back. So we didn't know that whether we would be like that or like that. It took a few hours for us to realize that actually we stayed a few hours in space, 2 hours. And we had other systems that demonstrated in 2 hours that we're still rotating and moving in different space because the magnetometer in particular was very sensitive, and we saw that. And after 2 hours, everything stopped. But we didn't know whether it stopped because everything was off or because we had touched the surface. And actually, as you know, so we are somewhere there, but we didn't know at that point. And so during all that was at night, of course, as usual. So it was awful because up to the next morning, we didn't know where we were, whether we had landed or not. So we reshuffled the entire operation sequences. We re-upload a new set of imaging, but then we knew that we would have only one chance. So we had to find the right gain, make the sort of bet on where the sun would be and that sort of things. And finally, at 7 in the morning, even a little, we had these images. And that was really amazing. We all cried because that's exactly what we wanted to have a landed bodies on a sunlit nucleus. We had that, and it was that camera, that one here. The next was even better, and I put together the two of them, and that was really the first image that we immediately released. We had our foot here on the nucleus. And so, okay, we had that. I mean, 20 years old, the older solar system body here, close by. It was not trivial. I mean, the success of the mission is not there, but it's part of the success. I mean, to be able to select a body and to get there. Okay, so and we have even here the concert antenna, which is on the ground here. It touches and you have the shadow here. Good, so we had a dream until November 12th, and the dream was to land, and again, to try to understand the process and all that sort of things. And it became reality, the 13th. So we had done something. And we had all the images that were taken during the descent that went afterwards. When you see at 15, an enlargement, so this is the lander during the descent, here and there and there. And this here is what has been shown here, before and after, and that's really interesting. And that's a few minutes after touchdown, the lander was in the open space. So that was awful. But when you take that before and after, I like that because, you know, you see here something which is the images of the, okay. And this is exactly at the size of our lander here. So we could image the place where we were, moving a lot of material here. And actually, this is very important because the rebounds, we had 3 rebounds actually, 2 hours in space, as I said. It put a lot of add-on science, which was very interesting. Why have we rebounded? It tells something about the physical properties. And because we had planned 10 hours of observation, most of the instruments just ran normally, although they should have run on the ground. Some of them ran in space. But thanks to that, we have a lot of information there, and I will just say a few. First of all, at touchdown, we have a cloud of grains that went. But the grains are essentially the carbon-rich grains. And because 2 instruments we had on board, Ptolemy and Kozak, which are 2 mass spectrometers, one the time of flight and the other was chemistry, some of the grains enter the pipes of these instruments. And this has been measured in space instead of being there. But these are the most important results up to now of the carbon-rich material ever found. Unfortunately, the paper had been submitted to Science and not printed yet, so I will not tell you that it's very interesting. But it is very interesting. And with mixtures of a lot of nitrogen compounds and mixtures of aromatic and aliphatic materials. But by 2 or 3 weeks from now, you should have these released, I hope. Interestingly, of course, we have measured that, and then we went to rest, as you know, and so we have redone the experiments afterwards. When we went to rest, we couldn't find essentially by the sniffing itself, I mean, what is outside the nucleus at a given, there is no more carbon-rich material floating in space. In other words, because it was at 3 AU, essentially CO2 and H2O are the material outside, but it's because of the touchdown that mobilized this grain that we have access to this carbon-rich material. One of the questions, of course, is what is this surface made of? And one of the ideas that if we rebound it, it's because the material at the surface is different from the material inside. Not in terms of the composition, but on the structure itself. It's what I call the thermal sintering. Because of the passage at perihelion, you have some sort of sintering, but not by pressure, but by temperature, that made a sort of trampoline effect there that allowed us to dump a little bit. And because of dumping, the escape was at a velocity lower than the escape velocity. We rebound at 0.35 meter, 35 centimeter per second. So we could follow that. And so there is a modification of the surface of a comet just by the passage of perihelion, which in itself is interesting. There is another result which is very important, I think, for most of you here in the room. We had this boom deploy with a very, very sensitive magnet there, which measured not only the magnetic field, but the 3 components of the magnetic field very accurately. It was done essentially to measure the evolution of the interplanetary, the solar wind magnetic field. And so it could measure the potential remnant magnetization because it was on from the orbiter down to the descent and then continuously during the rebounds up to the point it went to rest. So we have a measurement of the magnetic field from all the distances from kilometers down to a few centimeters. And the important result is that there is not a single modification of the magnetization. There is no remnant magnetization in this nucleus. This is sort of fundamental because you might be aware that many people thought that the initial material would have been essentially magnetized at the time the collapse went, and that would have been a driving effect for the accretion itself in the, around the magnetized sun very early on. It's not the case. If you go down to scale, which is typically a few tenths of centimeters, I would say, because that's the distance at which we are now, there is no magnetization. It's a random, essentially. So that's part of the result that we've got already. But of course, finally, we went to rest. And that was really spectacular because, okay, these are the 2 images that I showed you. But when you see from where they were taken, then we went to this one. And these images, we saw a foot, but nothing behind. When we stretch here, So again, these cameras are very good, really, I should say, because you have only 8 DN, digital unit, out of 1,000. You stretch that, and immediately you see that actually there is something here, but it's backlit. The sun is over here, and we have a cliff here. And when you expand a little more, that's the cliff that shadows us for the moment. So, and what you see here is the reflection of the feet on these. And as you will see, I will show that you have structures here. These are really important because these are blocks of ices loaded with the organics, which is really the growl, our growl, really, to see the pristine material as it is, as it was, and we have it really at reach. Okay, I call that the perihelion cliff because of that, you know, normally if we had stopped at the place we touched down, at that point now in time, end of March, we would be dead because the temperature would be over the maximum temperature allowed by our system. Thanks to that, exactly the opposite. We are very cold now. It might be a problem, but supposedly we will wake up, and I hope we will. Then we can, in principle, be operational up to the perihelion, because then the shadow is sufficient to protect us against too much heat. We'll see that. Then we have another one, which this one now, we have an antenna and just nothing here. And you can stretch, we have the glare, because essentially these come from the reflection of the sun on our camera here. Okay, and the 3 others are essentially in the shadows. These are only 2 DN, so you have to stretch a lot to see things. I will, go rapidly now. And so we have landed, but when you reconstruct the way we have landed, it's very strange. This is the sort of things we have, and this is the images that we rapidly built, considering that we are in that sort of situation, probably. Actually, these are the drawings that I put on the blackboard in real time when I said, well, that would fit the best with the images we have. And so it was a little astonishing, but that's the reality. And now we have made some of 3D stuff that I will go rapidly. That's probably the way we are. We are in a big hall. It's artist view, no more than that. But that tells you the sort of things, still hot, right? You can see here. That's the place where we are. And this is interesting because this is what we call the panel 2. That's the only one for the moment, or in November, making electricity. All the rest was in shadow, essentially. Only this one was lit during an hour. The rotation of the comet is 12 hours. The day is 12 hours. We have electricity only during 1 hour and 10 minutes because of this. Because of the shadows everywhere here, all these panels do not produce any electricity, essentially. But the real problem is not there. The real problem is that on that side here, you have 2 black things here, which are absorbers, which are the ones which normally take the photons to heat up the interior to maintain the temperature interior, which is over minus 45 degrees, which is the minimum temperature at which our computer can be rebooted. And the problem we have is, for the moment, we are probably lower than that because we are not well illuminated by the sun, which comes from here, essentially. Good, so these are the views. And that's probably where we are in a hall. We'll see. Good, so we have landed, but we have a lot of results. I've given you some of them. The most important, I think, is the fact that we are shadowed, but actually the cliff is like that. So the sun goes over the horizon, somewhere here. We think that if we are in the 1000 latitude, because we're entering spring now, the sun is already over this cliff. So probably we are sort of well illuminated for the charging. For the charging is fine, but the absorbers are not well illuminated, so the temperature is probably a little too low now. Okay, so why are we so eager to be there? Now I stop, yes. It's because when you see that sort of things, we have a lot of different material here, from the grains up to these, which are really similar to the sort of thing that we see from large distance, which are the icy blocks, very low albedo, loaded with organics here. And so, just to finish with, we have a huge variety of materials within a few tenths of centimeters from our system now. And so the final side is really much better than every one we could have hoped of, because really that's the side in which the material that we have access to is the one we wanted to. It's the most pristine material in the solar system we could have access to. We have the ices, we have the organics, we have everything there. And we know that the location as we are here, because we have the capability to rotate the lander with respect to the feet, we will be able to drill in that material supposedly we wake up. So the question is, shall we wake up or not? And the first set of tries were up to last Saturday. It was last week, actually, that we tried, from March 12th to 19, 20. It was not successful. There are different possibilities, but probably the most likely that the temperature inside is not sufficient for the moment to make the reboot of our system. So we'll retry a few times, of course, I mean constantly, but we have to have good opportunities between the orbiter there, sending messages to us, and Philae responding possibly. So that will be in 2 weeks from now, the next. And then during May, all May, we'll have a lot of different possibilities. So the goal is really to try to, the hope is that Philae will be in a good shape. I've maintained, we are sort of convinced that low temperature is not an issue to survive, for the material to survive when it's not operating. The problem is that we need to have sufficient solar input inside to heat up the system up to minus 45 degrees, because the interior, some of the material inside has to be at that temperature to be able to reboot. If that's the case, the energy should be sufficient. I've not given numbers there, but I will finish by that, for you to have an idea of the sort of challenges. We have 10 instruments on board, 2 mass spectrometers, 1 drill, for example, supposedly to drill that size, 30 centimeters, in something as hard as concrete. So 30 centimeters in concrete, you will to drill. 10 instruments with 2 high voltage, 3 high voltage with magnetometer, 7 cameras, a lot of things. For all that, the power we have varies between 5 and 10 watts, which is very, very limited, right? If you want to buy a place where to make hole in a drill, you will not go and ask for a 5 watts system. Our drill is 2 watts. And so we have to work with so low resources that, again, it's a very risky mission, but it copes with the ambition we have to analyze for the first time this pristine material. I will stop there.